It was a year ago today. Yeah. Oh, so we're working on example 4 from last class. We have an equilibrium mixture of iodine, hydrogen, and the product HI. So iodine, hydrogen collide, and they break those bonds and make HI. At the same rate, HI is decomposing back to these original reactant molecules. We achieve an equilibrium state, and we know at this particular temperature, that's a Kelvin temperature, the equilibrium constant, another capital K, is known. We also know some initial pressures. So these were pumped into the container without any product there. And according to a Q value, which is just 0, because the numerator here would be 0 in a quotient, we know we have to make some product to reach equilibrium. So essentially, we're just trying to find the equilibrium partial pressures of these 3 gases. Remember this ice table. We first write in the initial pressures of each, and then we predict how they're going to change by knowing this Q. And then this represents the equilibrium pressure. So we have to solve for X. So we said, hey, equilibrium pressures, that's what goes into a K expression, this ratio. So we could put our 2X in for the product and square it. And then we plug these in for the reactants. We have this ratio where we know it's equal to 92.6. Okay, so we have to solve for X. So we have to do like a little algebra. So maybe the first thing is to go ahead and multiply both sides of this equation by the whole denominator. So we get something like that. So we've got this, oh, and then we have all this distributing to do. So when we distribute, like say the 92.6 times that, and then the 92.6 times the negative X, we're going to get like a 183 minus 92.6x. So we have that quantity times the 1.71 minus x is equal to 4x squared. Remember that 4, I got it from squaring the 2, squaring the x. And then we have to multiply these two, and this one, and then we have to do that one. So we need like 4 terms here. The first, the outer, the inner, and then the last. So I need 4 terms. So if I write those out, I'm going to get this like 313 minus 183x minus 158x plus 92.6x squared. That's the last term there. And on the right side, still got that 4x squared. So then the next step is just collect like terms. Collect the x squared terms, the x to the first terms, and then the constant. So when I do that and put it all on the left side, I've got 88.6x squared minus 341x plus 313 is equal to 0. I brought everything over. So you should try that. Make sure you get those numbers. Now I'm just going to look at the coefficient of my x squared. I'm going to underline that in blue. And then the coefficient of my x to the first, I'm going to underline that there in green. It also contains that negative sign. And then my constant term without any x is, I'm just going to underline that in red. So what I have here is I want to solve for that x. I have x squared. This is a polynomial. This is also called a quadratic equation. It's in the form of some constant times x squared, constant times x, and then a c, like just nothing times, or there's like x to the 0 there, is equal to 0. So that's a parabola. And it's quadratic, it's meaning it's an x squared term. So the formula to solve for x here, it's very convenient, is to go ahead and use the quadratic formula. So we just have to look at these coefficients here, this blue one, the green one, which contains a negative, and the red one. And we just plug it into this formula. And notice the formula is plus and minus. So we put it all in with the plus, and then we put it all in with the negative. We're going to get 2 x values, 2. And so what does that mean? That's saying that this parabola is going to cross the x-axis, set equal to 0, in 2 places. Like there's 2 roots. You know, maybe it looks like this, maybe they're both positive roots. I don't know until we solve it. Sometimes you get imaginary roots, but hopefully not in this work. I can imagine. Okay, so we plug it into the formula. So x is equal to negative b. Our b is also negative. So it's negative a negative 341 plus or minus the square root of our negative 341 squared. That's b squared minus 4 times the a times the c. And then that entire thing is over 2 times the a. Yep. So you have to solve that. One way to, you know, after you do your work to see if you've made any mistakes is you could check your solving. You could find any number of different places on the internet that can solve it for you, like mathpapa.com. That's a fun one, mathpapa.com. So you can type in an equation just like this, and it will solve it for you, and that helps you to check your work. So the two roots I get are 1.50 and 2.35. So there's the two roots that I get. Now, you might get just slightly different, or Math Papa might tell you just slightly different, because it's all about the rounding. If you have too much rounding in the intermediate steps, you're going to get some numbers that are just slightly different in the second decimal place. So I just try to maintain kind of some numbers here. I didn't write out a whole bunch. Ultimately, we're only allowed 3 sig figs in our final answer. Now, we have two x values, but not all of them are, you know, not both of them are going to make sense to us. Turns out they're both positive. So like this parabola, you know, is both crossing over here. So there's like a 1.50 and a 2.35, you know, but that's the math part. But we want to know what makes sense physically. So if we go over here for our x, I mean, are we going to choose the smaller or the larger? Like if we chose the larger 2.35 and we try to put it in here, like 1.98 minus 2.35, that would give us a negative pressure. Well, that doesn't make sense physically. So we're not going to use that one. We're going to use the 1.50. There's only one that will make sense physically. So when we plug in our 1.50 for x in each spot there, then our equilibrium partial pressure of I2 comes out to be 0.47. And for our H2 comes out to be 0.21. Or 20, I'm sorry, 20. And let's see, no, I think it is like 2.21. See, I'm kind of going back and forth because it all depends on the rounding. So I'm going to pick one. Okay, so it's 0.48, could be like 0.47. It varies in that second decimal place, 0.21, and then like a 3.01. We'll go. All right, so here's my equilibrium pressures. Great. Now we could ask another question about this equilibrium situation, which is a common question that is asked. And that's after you find the equilibrium partial pressures, then you often want to know something about the reactant. Like you might ask in terms of percentage. What percent iodine is unreacted in the mixture? You know, we have this mixture. So when we say unreacted, we're talking about what remains at equilibrium. So it's like we want to know the pressure exerted by the iodine, what it is at equilibrium compared to what it started with, the initial pressure. So it's like part over whole. That's what a percent is, part over whole times the 100%. So our equilibrium pressure here, like if I pick that 0.48, over my initial pressure for the iodine, 1.98. You know, that's quite a bit there, times 100%. So 0.48 divided by that times 100% gives us a 24%. That's what is left. in the mixture. 24%. So quite a lot of it actually reacted. So 24% is unreacted, and so that means 76% reacted. Okay. Yes, so 24% is left, 76% reacted. So more of it disappeared and became product. And, they still go back and forth, but the composition of the mixture shows us we have majority product. And that's what a K value larger than 1 tells us as well. All right, so this is a pretty common question. We're going to be asking this kind of percent question. It's a way to compare quite a bit in problems in this chapter and also in our next chapters. Okay, so I have another example. Wait for some notes. This example, we have a situation where we had an x squared term. So we had a quadratic equation to solve. But sometimes if we get some more complication here, more reactants and products and different mole ratios, we could actually have polynomials to solve that are larger than x squared. We might have x cubed or x to the 4th, and have to solve those. In that case, we don't use a quadratic formula. We usually just plot that to find where the roots are. So just to highlight this example, we have a value for K here, and our job was to find the equilibrium pressures exerted by each species in the equilibrium mixture. Our past examples from last class, it was the opposite question. Given the equilibrium pressures, because they were measured just like you did in lab, we had to simply place those into the ratio and find a value for K. That was actually a little easier math-wise. When you have to find a value for the equilibrium constant, given the equilibrium pressure values, it's a little bit quicker. This example, oh wow, if we know the K, then we have to find the particular composition at that temperature. So let's try another example. So write down the reaction for this example. We've got some carbon dioxide and hydrogen. We put them in a flask and we make some carbon. It looks like if you write down this reaction, it's all 1-to-1 mole ratio. A K value is given, so it had to be done under some constant temperature conditions. And similar question to our last example, find the partial pressures of each gas in the mixture at equilibrium. All right, so we've got some initial pressures, 2 atmospheres, 1 atmosphere. And then we're just going to say, well, if there's no mention of carbon monoxide and water vapor, then that means initially there's none. And so a Q value here would be equal to 0. So that definitely means we're going to have to make some product. Make product at the expense of the reactants. So this is going to decrease, and at equilibrium, it's going to end up decreasing by some amount. It's a 1-to-1 mole ratio, so this will decrease by the same amount, X. See, I put my decrease right there. And these are going to have to increase by 1-to-1 mole ratio. They're going to end up as X. And so this is the row here. It goes into the K expression, which is 0.64. And if we have to find the partial pressures, we need a value here, So that means we need X. Oh, okay, so in our ratio, we got the pressures of the products. They're both X, so that's going to be an X times X. And the pressures of the reactants, everybody's here, mole ratio is all 1. So we got 2.0 minus X times this one. There. So we got to find X. So it looks like this is going to be a quadratic equation. So we've got to simplify this fraction, collect your terms, get it in the quadratic form to get an A and a B and a C. Solve for X. We get 2 possible X values. Then check your work with mathpapa.com or something else. And so when you solve for X, then you'll be able to plug it in here. So I have a quiz I'm prepared for you on Brightspace. And on the quiz, you're going to need to report the equilibrium pressure of carbon monoxide in this reaction. So that means you're going to have to report the X value that you solve for. Okay, so work on that piece. Now, back to example 1. So if you look back in your notes to example 1, you can pause the video while you find your notes. But we worked on this one where we, this is our very first example, example 1, where we looked at a mixture that temporarily contained all 3 gases, and we tried to find if it was equilibrium. So I want to remind you of this. Because now we've built some skills here. So I got to review this. So in our ice table, remember this is the initial change in equilibrium. These are the initial pressures of all 3 gases. So we actually had to calculate Q to determine not only if the mixture was at equilibrium, but if not, what has to happen for it to achieve equilibrium. So we had to put the products over reactants in here, and we found a Q value equal to 34 and compared it to the known K value of 26. It's too much. So this time we had to make more reactant. We needed a plus here. Our other examples, we had a minus on the reactant change. So we have to make more reactant at the expense of the product. So that's about where we left that example. So now we have the ability, now that we've done these examples, we have the ability to find the equilibrium partial pressures of each of these species. Right? So you just add the 2 rows here to get this last row. And then we have to set up our K ratio. So K is known to be 26. And so we need the products, product pressures, product amounts in terms of partial pressures, minus X, right? Get 0.45 minus X. There we go, we fix that, over 0.012 plus X. So I've got products over reactants. Okay, very nice. So this again is going to be a quadratic equation once we figure all that out. So, so you're going to need to calculate it, check your work with good old mathpapa.com or another piece, or maybe just your graphing calculator has a way to just solve a quadratic equation. So in the quiz that I've prepared for you, I will also ask you to tell me the equilibrium pressure exerted by the phosphorus trichloride product here. So if you solve for X, you've got to subtract it from 0.90. So that is also going to be on the quiz. Okay, and that's all we have. Thank you.